Ma.
Okay, should I begin with the session?
Yes, please.
Okay, so can everyone see my screen and hear me clearly?
Yes, ma'am.
Okay, so good evening, everyone. Welcome to today's physics session. We're going to be doing momentum and impulse. So here's the first question that we're going to look at. So question 1 says, dancers have to learn many skills, including how to land correctly. A dancer of mass 50 kilograms leaps into the air and lands feet first on the ground. She lands on the ground with the velocity of 5 meters per second. As she lands, she bends her knees and comes to a complete stop in 0.2 seconds. 1.1 is calculate the momentum with which the dancer reaches the ground. Okay, so that one, for 1.1, the momentum is equal to mass times velocity. Okay, and then they told us that her mass is 50 kilograms. So for M, it's 50 kilograms. And she lands on the ground with a velocity of 5 meters per second. So that's 5. So she's jumping towards the ground. So if I'm taking downwards to be positive, so I'll just do that. Downwards as positive. Then in my substitution here, I just have +5. Okay, and then the answer that I get is 250 kilogram meter per second. Okay, and so because it's positive, it's just downwards. Okay, if you had chosen upwards to be your positive direction, then you would put in -5 here, and your negative value would tell you that the momentum is downwards. Okay. 1.2 says, define the term impulse of a force. Okay, so what is the impulse of a force? It's just the product of the net force, the product of the net force and the time interval during which the force acts. Okay. The product of the net force and the time interval during which the force acts. Okay, so that's 1.2. 1.3 is calculate the magnitude of the net force acting on the dancer as she lands. Okay, so what's the net force that acts as she lands? And for that, we know that the net force multiplied by the time interval is equal to the change in momentum. Okay, and we're trying to find the net force. So that's the net force. And the time interval is 0.2 seconds, because that's what they told us. And then the change in momentum. So she stops. And just before that, we calculated it to be 250. Okay. So if you do this calculation, then you will get that the net force is equal to minus 1250 newtons. Okay, and then the question said calculate the magnitude of the net force. So then you just say that the net force is 1250 newtons. Okay, that's just the magnitude. The negative sign's telling us about the direction. Okay, so that's the net force that acts on the dancer as she lands. Excuse me. So then it says, assume that the dancer performs the same jump as before, but lands without bending her knees. Okay, and so 1.4 says, will the force now be greater than, smaller than, or equal to the force calculated in 1.3? Okay, so in 1.3, the force is 1250 newtons. And if she didn't bend her knees now, what will the force be? Greater than, smaller than, or equal to? And the answer is that the force will be greater than. Okay, greater than. The next question says, give a reason for the answer to 1.4. So why is it going to be greater than? So you also know that if you're jumping off a high wall or from any high position, when you jump, you always land and bend your knees. So you fall all the way down. You do not land with your legs straight. And the reason you do that is you want to increase the time that it takes to stop you. Okay, so that the force that's acting on you will be smaller. So if you keep your knees straight, then the force is going to be greater. And the reason for that is you've got the same change in momentum, right? So I'm just going to write here, for the same change in momentum, the stopping time, or the, I'm going to call it the delta T. The delta T will be smaller, because if you're landing without bending your knees, you're going to come to a stop much quicker than if you bent your knees and went down. So for the same change in momentum, the delta T will be smaller. And therefore, the upward force, or the net force, I'm going to write it as F net. The net force will, or the net force exerted on her will be greater. Okay, so that's if you just look at this equation, F net is equal to delta P. Okay, so then delta P is equal to, oh, sorry. From here, F net is delta P over delta T. F net is equal to delta P over delta T. So just by looking at this equation, you can see that if delta T is smaller, then F is going to be bigger. So when you bend your knees, when you land, you're making delta T bigger. And if the denominator gets bigger, then the net force will be smaller. And that's what you want. You want a smaller force acting on you so you don't hurt your knees. Okay, so that is question 1. Are you happy with that? Are there any questions? Okay, can I go on to the next question? Oh, sorry.
Ursula, in the chat quickly, Erica would like to know what year or which year the questions are coming from, which paper?
I think this is from a 2020 paper.
Okay, and then Nomonde would, if you could please explain 1.4 again, the greater than, smaller than, or equal to.
Okay, sure. Okay, so question 1.4 is, okay, so firstly it said that this dancer is landing with a velocity of 5 meters per second. As she lands, she bends her knees and comes to a complete stop in 0.2 seconds. Okay, so when she lands and bends her knees, it takes 0.2 seconds for her to come to a stop. And then we calculated in 1.3 the net force that acts on her when she does this. The next question, 1.4, says, if she jumps as before, but lands without bending her knees, how will the force be on her now? Will the force be greater than, smaller than, or equal to the force we calculated? So if she lands and bends her knees, the net force will be 1250 newtons. If she lands and doesn't bend her knees, then she's going to come to a stop much quicker, which means the delta T is going to be smaller. And if you look at the equation now, if I write it out like this for the net force, you can see that the time interval is in the denominator. So if the time is smaller, then the net force is going to be greater. So if she lands without bending her knees, then delta T is going to be smaller and the net force on her will be greater. Okay, I hope that's a little bit better.
Sorry, ma'am, I also have a question.
Yes.
So ma'am, I wanted to ask for 1.3, if maybe you take down as negative, were you going to get a positive answer for your F net?
If you are taking, yes,
Down is negative.
so when you choose this, the signs, yes, so correct. So what you do is whenever you're doing these problems, you choose one direction to be positive, whichever one you want. And then you substitute those values into your equation. And if you get a positive answer, then it means the direction that you chose is the answers in the same direction that you chose. If you get a negative answer, it means it's in the opposite direction to what you chose as positive.
Okay,
So yes, you
thank
can
you.
choose whichever direction you want. You're
Okay,
welcome.
thank you.
Okay, are there any other questions?
I think you can move on to the next question.
Thank you. Okay, so this is question 2. Percy, mass 75 kilograms, rides at 20 meters per second on a quad bike. That's a motorcycle with 4 wheels, with a mass of 100 kilograms. He suddenly applies the brakes when he approaches a red traffic light on a wet and slippery road. The wheels of the quad bike lock and the bike slides forward in a straight line. The force of friction causes the bike to stop in 8 seconds. Okay, so 2.1 says, define the concept momentum in words. Okay, so momentum is just the product of, of an object's mass and its velocity. Okay, so momentum is the product of an object's mass and its velocity. So the velocity of the mass. Okay, that's what momentum is. Calculate the change in momentum of Percy and the bike from the moment the brakes lock until the bike comes to a stop. Okay, so calculate the change in momentum from the time that the brakes lock. Okay, so the first thing we're going to do is choose the direction. So I'm going to say that the direction in which he's traveling. So the direction of motion is positive. Okay, so the direction in which he's going is my positive direction. And now I want to find the change in momentum. So delta P, that's just equal to my final momentum minus the initial momentum. And then that's just final is mvf minus mvi. Okay, and then they said here that his mass is 75 kilograms and the bike is 100 kilograms. Okay, remember it comes to a stop and it said calculate the change in momentum of Percy and the bike. So the mass is going to be, or I can also just rewrite this as m vf minus vi. So then I can write this as 175. And then the final velocity, it comes to a stop, minus the initial velocity. And I'm writing it here as plus 20 because I'm taking the direction in which he's traveling to be positive. Okay, so you could just say minus 20, but I'm writing it like this to remind you that the 20 is positive. Okay, and so if you put this into your calculator, you should get minus 3,500 kilogram meter per second. Okay, so it said calculate the change in this. So what does this negative sign mean? It means that the momentum changed in the direction opposite to the direction of motion. Okay, so delta P is equal to 3,500 kilograms meter per second opposite to the direction of motion. Okay, so that's the change in momentum. The next question is, calculate the average frictional force exerted by the road on the wheels to stop the bike. Okay, so we've already just calculated the change in momentum. They told us that the bike comes to a stop in 8 seconds. And now they want to know what's the average frictional force that was exerted to stop the bike. So similar to the example we did before this, we know that the net force multiplied by delta T is equal to the change in momentum. So we're trying to find the net force, which we know is friction. So I'm writing it as a small f. Delta T is 8 seconds. And delta P we just calculated as minus 3,500. And then if you do the calculation, you'll find that the frictional force is equal to negative 437.5 Newton. Okay, so what does the negative sign mean? It says that this is in the direction opposite to what I chose as positive, right? So the frictional force is equal to 437.5 newtons opposite to the direction of motion. Okay. Okay, so this was a short question. Are you happy with that?
They mostly seem happy in the chat. We'd just like to know if there are no other forces present.
No, there's no other forces. They didn't tell us about any other force. And they said wet and slippery road, but they said the force of friction causes the bike to stop in 8 seconds. So those are the only forces. Well, that is the only force.
Okay, that looks like it. I think other questions have been already answered in the chat. So I think you can move on unless somebody unmutes.
Okay, thank you. Okay, so here's question 3. This one's a little bit different from the other 2 that we've done. Okay, so 2 stationary steel balls, A and B, are suspended next to each other by massless, inelastic strings as shown in diagram 1 below. Okay, so the first diagram. Ball A of mass 0.2 kilograms is displaced through a vertical distance of 0.2 meters, as shown in diagram 2 above. When ball A is released, it collides elastically and head-on with ball B. Ignore the effects of air friction. Okay, so you need to just take a moment to look at the picture and understand what's happening. Okay, so 3.1 says, what is meant by an elastic collision? Okay, So for 3.1, what's an elastic collision? So a collision, okay, I'm gonna have, so an elastic collision is a collision in which both total momentum and the total kinetic energy conserved. Okay, a collision in which both total momentum and total kinetic energy. You write it like this, eh? EK. Total momentum and total kinetic energy are conserved. And very often when they ask us a question like this beforehand, then we need to know this for the next bits. Questions that follow. Okay, so immediately after, so let's just remind ourselves again. So ball A of mass 0.2 kilograms is displaced through a vertical distance of 0.2 meters. When ball A is released, it collides elastically and head-on with ball B. Immediately after the collision, ball A moves horizontally backwards. So to the left, ball B acquires kinetic energy of 0.12 joules and moves horizontally forward. So to the right. Okay, that's what's happening. And now they want us to calculate the kinetic energy of ball A just before it collides with ball B. And it says, use energy principles only. Okay, so now we need to calculate the kinetic energy of ball A. So that's 3.2. So how are we going to do that? They said use energy principles only. Okay, so for ball B, we're going to use the conservation of mechanical energy. So we're going to have that the kinetic energy plus the potential energy at the top, so that's just before it collides, must equal to the kinetic energy plus the potential energy at the bottom. Okay, I'm just writing it like that. Okay, so then let's go and calculate it. So kinetic energy is a half mv squared plus potential energy is mgh, and all of that is for the top. That must equal to, again, kinetic energy is a half mv squared plus potential energy is mgh at the bottom. Okay, so now we can substitute the values we know. So for this one here, a half mv squared, remember the ball is released. So v here is 0, but I'm just gonna write it here as a half. The mass is 0.2. Okay, kilograms, and v is 0. So that whole term becomes 0. Plus at the top, so mgh, the mass is 0.2, g is 9.8, and at the top it was 0.2 meters. Okay. Then that must equal to, now a half mv squared at the top, I'm just going to call that again EK because that's what I'm trying to find. The question is to find this kinetic energy. Okay, plus mgh. M is 0.2, G is 9.8, and at the bottom, H is 0. Okay, so just to show you, this 0.2 that we measured is from the 0. So when it knocks ball B, the height is 0 at the bottom. So that whole term cancels. Okay, so this whole term is 0, and that whole term is 0. So if we look here, we've just got EK is equal to 0.2 times 9.8 times 0.2. So that just tells us that the kinetic energy is equal to 0.39 joules. Okay. That is the kinetic energy of ball A just before it collides with ball B. Okay, so just before it collides, that's the kinetic energy of A. Okay, so maybe I should have said here for ball A. Maybe I should have did that at the beginning for ball A. Okay, so that's the kinetic energy of ball A just before the collision. 3.3 says, calculate the speed of ball A immediately after the collision. Okay, how do we calculate the speed immediately after the calculation? Okay, so again, we're going to use our energy principle. So this is 3.3. Excuse me. Remember, they told us that this is an elastic collision. Okay, and that's how we can say that EK before is equal to kinetic energy after. Okay, the kinetic energy before the collision is equal to the kinetic energy after. Okay, but now we're going to say the sum of the kinetic energies because we've got ball A and ball B. Okay, so what is the initial before? It will be the kinetic energy, and I'm going to call it I for initial, of A plus the kinetic energy initial of ball B must equal to the kinetic energy final of A plus the kinetic energy final of B. Okay, so that's the important part, is writing out the equation like that. And once you've got that, now we can substitute the values that we have. So initial kinetic energy of A, that is what we've just calculated now, 0.39. Okay, so I can just substitute your 0.39 joules. What is the initial kinetic energy of B? B is stationary, so V is 0, so a half mv squared is just 0. And that is equal to, what is the final kinetic energy? So that's what we're going to try to find the speed. So the final is going to be a half m. So we talk about ball A, so it's mass of A, V final of A squared plus, what is the final kinetic energy of B? They told us here, B acquires kinetic energy of 0.12 joules. Okay, so they gave us the value here. So this is 0.12. Okay, we know the mass of A. So the only unknown is the V final of A, which is what we're trying to find. Okay, so if you do that, then you'll find that V final of A is equal to 1.64 meters per second. Okay, that's the answer to this question about what is the speed of ball A immediately after the collision. And that's what it is. Okay. Okay, the next question says, calculate the magnitude of the impulse on ball A during the collision. The magnitude of the...
Sorry,
Oh, sorry,
Ursula.
yes?
No, sorry to
Yeah.
just jump in. There are a couple of questions that are building up in the chat. So
Okay, yes.
the first one is, are all the questions going to be from 2020?
Today's the last session for the physics, isn't it?
On the current thing, I believe so, yes.
Yeah. So there aren't anymore. I do not know for the paper 2 which paper they are using for the chemistry part. But today's our last session, so we don't have another session for me to use any other paper.
Okay, that was the first one. The second one is if you could just go a bit more up and down between the question and your solution when you're explaining, because some of them were getting lost when you were doing 3.3, I think, or 3.2, in terms of they couldn't remember what the picture looked like. And I suppose Kai wants to know if we're going to be doing work, energy, and power.
No, today was just momentum. And so the energy equations that we use to calculate these problems with in momentum.
Perfect. And then Matle asks if you can please explain how you got to the answer for 3.3, I think it was, is what you put that up.
Oh, okay.
If you can just walk it through 3.3 again, and that's it for now. The rest have been cleared.
Okay, thank you. Okay, so yes, let me leave this picture on here for a bit longer so that you can see what's happening. So in here, we can see in diagram A, the two balls are just stationary there. We lift ball A up 0.2 meters vertically, and then we release it. It smacks into ball B. When it does that, ball B acquires some kinetic energy of 0.12 joules. Okay, and then the questions they asked us were, what is the kinetic energy of ball A just before it collides with ball B? And it said use energy principles only. So because they told us to use energy principles only, that is the only method that we must use. Any other equation, even if you're using work energy theorem or whatever, but you can only use the energy equations. Okay, so then to find the kinetic energy of ball A, we used this bit here, this equation, conservation of mechanical energy, and we found the kinetic energy of ball A just before the collision. For 3.3, it wanted to know what is the speed of ball A immediately after the collision. Okay, and they told us that the ball collides elastically. So that was important. So here it is now. We know the kinetic energy just before collision. They want us to calculate the speed immediately after the collision. Okay, so the way we do that is to say that the kinetic energy before the collision is going to equal to the kinetic energy after the collision. And so the kinetic energy before is the kinetic energy of ball A plus the kinetic energy of ball B. That must equal to the final kinetic energy of ball A plus the final kinetic energy of ball B. Okay, so the initial kinetic energy of ball A, we got it from the first bit of the equation. Okay, we calculated it there. The initial kinetic energy for ball B, because it's just stationary here, V is equal to 0. So a half mv squared is 0. So the initial kinetic energy for ball B is just 0. Then what is the final kinetic energy of A just after the collision? We don't know what it is. So we write it as a half mv squared. Okay, so a half MAVA squared. And this is what we're trying to find, the final speed. Okay, plus the final kinetic energy of B. So if we go look up here, they said that ball B acquires kinetic energy of 0.12 joules. Okay, so they told us what the kinetic energy is. So then when we go back here, we just fill in that value. Okay, so let's just do some missing steps then. So from this equation, if I just rewrite it, we've got 0.39 plus 0 is equal to a half MA V final of A squared plus 0.12. Okay, so I can rewrite that as 0.39 minus 0.12 is equal to a half. And okay, instead of writing MA, I know that A is 0.2. Is it? Yes, ball A of mass 0.2. So 0.2 VF A squared. So I'm just trying to find VF A. I can write it as squared, then it's just going to be 0.39 minus, I don't have my calculator with me, but you can, so I'll just write it like this. Just showing you all the steps. Then you divide it by this, yeah, divided by a half of 0.2, which is 0.1. But doing it like this, so you can see the steps. And then if I just want to take the square root of that, that's what that is. If you do it, you should get this answer here. Okay. So square root of 0.27 over 0.1. Is that better? Okay, can I go on to 3.4?
I don't have anything in the chat that hasn't been answered. So I think you are free
I thought I
to.
got cut off again.
No, it's still it. So you are free to continue, I think. Just a reminder from Dogozo that they should please sign the register as well as the feedback form.
Okay. Okay, so let's do this last bit. So now we've calculated, so just an overview of this. We've calculated the kinetic energy for ball A just before the collision. And now we've calculated the speed of ball A just after the collision. Okay. And then question 3.4 says, calculate the magnitude of the impulse on ball A during the collision. Okay. I'm leaving it here for a bit. So calculate the magnitude of the impulse on ball A during the collision. Okay. So how are we going to do that? They want us to calculate the impulse on ball A. So we can, this is 3.4. Okay, so for 3.4, I'm going to write in one part. So the impulse is equal to the change in momentum. Okay, so let me just write it as change in momentum, which is equal to the final momentum. It's equal to final momentum minus the initial momentum. Okay, and so if we rewrite that, it's going to be final momentum is mvf minus initial momentum is mvi. Okay, so for us to calculate this impulse on ball A, we need to know the final speed or the final velocity of A as well as the initial velocity of A. So we've just calculated here, this one here, 1.64 as the final velocity of A. But what is the initial velocity of A? We calculated here the kinetic energy of A just before the collision. So we have the kinetic energy here. This is the kinetic energy for ball A just before the collision. So we can use this kinetic energy to calculate the initial V for ball A. And that's what we will do. Okay. So I've got that the kinetic energy is 0.39. So you can see where that came from. The question is to find the impulse. And the impulse leads me to this equation here, but I do not know what VI is. I need to know this here. So I will come back to this equation, but first I have to calculate it. So I know that the kinetic energy of A is equal to a half M. So I can say initial, right? M, so it's MA V initial of A squared. And what is this kinetic energy? It's from here where I calculated it, 0.39 joules. So this is 0.39 joules. If I know what the kinetic energy is and I know the mass, I can calculate the speed. Okay, so 0.39 is equal to a half. The mass is 0.2 and VIA squared. Okay, so you know how to do that now. I'll just write out the equation. VIA is equal to 0.39 and then you divide the whole thing, divided by a half of 0.2 and take the square root. And then you should get 1.98 meters per second for the initial V of A. And I needed this to come back to this equation here because I'm trying to find the impulse. Okay, so now I've calculated V initial of A. And here I have V final of A. And I know the mass of A. I can calculate the impulse. Okay, so that's what I'm going to do. I'm going to go say here. So M is 0.2. So the only thing I have to be aware of here is the direction. Okay. Oh. So here I've got minus 0.2 and sorry. Minus 1.4 minus 0.2, 1.98. And if you put that in to your calculator, you should get 0.72. And for the impulse, it is F delta T, so the unit is just Newton second. Excuse me. Okay, sorry about that. Okay, so this is what we did. Oh. So when we are calculating this change in momentum, I remember what it said here. So I said you have to know which direction is positive so that you can put the correct sign in. It said here ball A of mass 0.2 collides elastically and head on with ball B. Okay, immediately after the collision, maybe I must just highlight this part here. So immediately after the collision, ball A moves horizontally backwards. Okay. So ball A moves horizontally backwards. The reason I'm showing you that is for you to see why I have the negative sign here, over here. Okay. So that was the last one. Do you have any questions?
I seem to have a question with regards to the negative sign for the final velocity. If you could please explain the negative sign.
Oh, okay. So this is what I'm saying now. So here for the final velocity, I'm saying that it's minus 1.64, right? So I calculated it here to be 1.64. But in the question, it said to me, and there's I've underlined it in red here, immediately after the collision, ball A moves horizontally backwards or to the left. So now it's going in the opposite direction. Okay, so to the right is positive, so the 1.98. So because it's backwards, it's to the left, then that is why I have the negative sign here. Okay, see my initial velocity is 1.98. So that's to the right. And so in here, it's a plus sign for the 1.98. And 1.64 is in the opposite direction. So the sign is negative.
Okay, and then that looks like it for questions. It's just if Ntokozo could please reshare the feedback link. Otherwise, I think you're free to move on to your next question.
Okay, I think we are done for time.
You are correct. It is 7 p.m.
Yeah.
The feedback link is a bit up in the chat. If you just hang around, I think Ntokozo will reshare both links in a moment, or let me try and reshare the link.
Okay, thank you from my side.
No, thank you, Ursula. I think that was instructive.
Thank you kindly.
Okay, guys. So Ntokozo has reshared the link for the feedback. The feedback, as I mentioned, is fairly important to us in how we work. So if you have suggestions or things that you'd like to see, or if you'd like to try and squeeze in another session before all of this comes to a head and you write your exam, please make sure that you indicate that on that link, because that's what we use in order to guide us in planning and prepping these sessions. Otherwise, I hope you found today instructive, and good luck with your studies, and hope to catch you on the next one. Enjoy the rest of your evening.